Hi guys, this video is going to be our second lesson in the geology unit, and it is about the evidence that we use to support the theory of plate tectonics. So a basic definition for plate tectonics, remember in the previous lesson about the Earth's interior and the layers of the Earth, we learned that the outermost layer of the Earth is the lithosphere, also called the crust, and that lithosphere is broken into chunks that move around due to convection currents that are occurring in the asthenosphere and the mantle. So there's two major pieces of evidence that we use to support the theory of plate tectonics, and the first one is called the theory of continental drift. So the theory of continental drift was proposed by this guy named Alfred Wegener, and he, looking at maps, was struck by how incredibly closely it looked like the coasts of South America and Africa fit together. He thought they looked like puzzle pieces, and so he thought, what if the continents used to be joined together into a bigger landmass and then for some reason, some way, somehow broke apart and drifted away from each other? And so he called this idea continental drift. So everyone in the scientific community was like, that is absolutely the most ridiculous thing we have ever heard of. You are an idiot. Buzz off with these stupid ideas. But he kept at it. He kept looking for more evidence. He unfortunately died really tragically. He went on an expedition to the North Pole to deliver supplies, and he never made it back. He froze to death on his way back from the base camp. And then a few years after he died, everybody realized, wow, he was completely right about this. There's a lot of evidence that supports this idea. Maybe we should have been nicer to him. So the main evidence that Alfred Wegener was looking at to support his idea when he was developing his theory of continental drift is called fossil correlation. He was looking at the fossil record, and he noticed that there's a bunch of different instances of the fossil of the same organism present on two different continents with like a ton of space in between them. So for example, this little guy, this Cynoganthus, or however that's pronounced, was a reptile. Fossils are found both in Africa and South America, and this guy had stubby little legs. There's no evidence to show that he was any good at swimming at all. So if he has fossils of him in South America and Africa, if this is what is in between South America and Africa now, the whole entire Atlantic Ocean, it's like, well, how the heck could he have swum across that ocean? If he evolved in Africa, how could he swim all the way across the Atlantic Ocean to South America and have died over there? It's just impossible. There's more examples of this with the mesosaur. The mesosaur was a freshwater reptile, so again, fossils of him in Africa and South America. He's freshwater. He couldn't survive in the salty ocean water, so there's no way he could swim across the Atlantic Ocean. Lystrosaurus, again, another stumpy land creature, but he's found all across a bunch of different continents with huge, vast amounts of ocean between them, so there's no way he could swim that far. It's not just animals, there are some plants that support this idea. This Glossopteris is a plant that has really heavy seeds that when they go into water, they just sink. So there's no way that the seeds of Glossopteris could float all the way across whole entire oceans to end up on different continents. Next type of evidence that we look at to support the idea of continental drift is called rock correlation. So now instead of looking at fossils, we're looking at rock types. So they have noticed by looking at rock samples that the Caledonian Mountains, which are of Western Scandinavia here, are exactly the same rock type as what makes up the British Islands down further south, but also exactly the same rock type as makes up the Appalachian Mountains of the eastern United States. So it's pretty clear to see that these rocks all formed in one place. This all used to be one mountain range, and then some force running through the center here pushed the two halves of the mountain range away from each other. The last piece of evidence that we use to support the theory of continental drift is called paleoclimatology, and paleoclimatology is the study of ancient climates. because as we know, the climate changes all the time. We've gone through different periods of ice age versus hot times on Earth. And we can see that there is significant evidence of glaciation on land that is now near the equator. So up here in the corner, this is a map of what land looks like now. And all of these white spots is where there's evidence of glaciation in the past. And so if the equator is running right along here, all of these places where it's showing glaciers like India, Africa, South America, Australia, where those landmasses are now, it's way too warm for glaciers to ever form. So like during the last ice age, the farthest that glaciers ever got down from the North Pole was like down towards Montana, Minnesota area. They never got further than that. It was still warm-ish near the equator, too warm for glaciers to form. So that evidence leads us to believe that if there were glaciers on that land, it must have been much further north or south at some point in order for the glaciers to have formed there at some point. And then also there's evidence of features called coal swamps in Canada. So Canada is really rich in like oil shale and different deposits of coal. And we know that coal and oil forms in really specific conditions that have to be warm. Coal especially has to have a specific kind of swamp that formed millions and millions of years ago in order for there to be coal present today. So if you look at this map here, you can see here's the outline of North America, and right up here is where Canada is. So look how much closer it is to the equator 306 million years ago compared to Canada would be way up here now in present day. So this is all just evidence that supports the idea that all of the land masses used to be in different places on the Earth compared to where they are today. All right, so remember I said there were two main pieces of evidence that we used to support the theory of plate tectonics. One was continental drift, which we just talked about, and the other is the theory of seafloor spreading. And the main idea of seafloor spreading is that there are these cracks in the middle of oceans where magma rises up and forms new sea crust, and as it forms new sea crust, like is going on right here, it pushes the old crust away. And so the seafloor is spreading apart and the ocean basins are getting wider. That's what this little guy is saying, like, oh, it's taking longer to fly across the ocean every time because of seafloor spreading. So now what that little guy in the airplane was saying in the cartoon on the previous slide was obviously exaggerated because the process of seafloor spreading happens at such a slow rate that it's really kind of impossible for humans to even notice that it's happening. It happens like maybe 5 centimeters a year the ocean gets wider by. But basic evidence we have that supports the idea that the seafloor is spreading, though it's happening so slow that it's hard to tell, is that we can observe new sea crust being created in the middle of ocean at what's called a mid-ocean ridge. So this is where part of the mantle gets hot enough that it melts into magma and rises up. And as it rises up, it pushes the two chunks of plate on either side of it away from itself. And so there's like an underwater mountain range here. That's what's called the mid-ocean ridge. So that's where new seafloor is created. And then at the other edge of the plate, the ocean plate is going to sink beneath some other plate. In this example here, it's sinking beneath the continental plate, but they can also sink beneath other ocean plates at a feature that's called a trench, and this process is called subduction. So ocean crust is created in the middle of the ocean at the mid-ocean ridge, and ocean crust is destroyed at the edge of the plate, at the edge of the ocean, at a trench. Second piece of evidence we have that supports the idea of seafloor spreading is called paleomagnetism. Paleomagnetism is a branch of science where we study the magnetic field of the Earth and what it's up to. Remember, you watched that video about the core of the Earth that talked about the magnetic field and how it's possibly going through a phase of reversal right now. And we can see that that's happened a bunch in the past, and this is the kind of data that those people are looking at. So there's this mineral called magnetite, which is a magnetic mineral, and it forms in the magma at the mid-ocean ridge, and then as that magma rises up out of the ridge and hits the cold seawater and cools, that magnetite is frozen, pointing toward wherever the magnetic north is. And so we can see stripes in the seafloor, like you can see in this picture to the right over here. We can see stripes of when there's normal polarity versus reverse polarity. Normal is colorful stripes, reversed is magnetic. And so this idea that new seafloor is being created and the seafloor is spreading away from the ridge in the middle is supported by these stripes of magnetic mineral in the crust. Okay, here's our very last piece of evidence that supports the theory of seafloor spreading, and this has to do with the age of the crust. So we can measure the age of a rock by looking at how much of certain types of radioactive isotopes are present in the rock. And so we can tell that the youngest pieces of ocean lithosphere are in the middle of the ocean near the ridges. So like this one right here, this ocean between North America here, Europe, South America, and Africa. This ocean is the Atlantic Ocean. And this is where the mid-Atlantic ridge is. This is the mid-ocean ridge that runs through the Atlantic Ocean. And we can see really clearly that the youngest rocks that are part of this ocean crust are in the middle of the ocean, and the oldest rocks are at the outside edge. So that supports the idea that the new crust is being formed in the middle of the ocean, and the older crust gets pushed away towards the edges.